All right, functions Monday morning. Spring break is over, and oh yeah, you. What's the symbol? Yeah, that was me. I wrote. Wait, just like
practice.
I don't know. Just like your. I have no idea what that is. I don't have a C in it.
Okay.
I don't know. What does that say? R-E-K-T?
Yeah.
You wrecked
it. Number wrecked. I don't know. It's some weird thing. It's pretty funny though. But I don't get the joke. All right. So Jesse, Matthews, David Miller, you are probably on some kind of exotic vacation. We are sitting here in class. You can get like a chair and stuff, maybe. And we're going to do some learning. What specifically are we going to do? We're going to go over the homework. I gave you a bunch of homework from 9.1, 9.2, and 9.3. How did that go? There was one like really cool problem. And then not so much after that. I mean, not so many easy problems. But we can do whichever. Yo. Sorry, which one? Yeah, 69 from section 9.1, right? Yeah, so on the section 9.1, okay, this is like a really cool problem. Let's do this problem. Here is what it said. It said, oh, first of all, it introduces you to the Fibonacci sequence in case you've never heard of it before. And it says, okay, here is, so this is number 69. Here it says, here is how the Fibonacci sequence works. The a sub n plus 2 is a sub n plus a sub n plus 1, and also a sub 1 and a sub 2 are both 1. Okay, so part A was just trivial. Is everyone caught up to where we are? Yeah. Okay, part A was just trivial. Part A just says, hey, write out the first 12 terms of the Fibonacci sequence. Okay, so you just do it. Like, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. Someone tell me when I can stop. 89, 140, 4.
236.
Okay, good. Okay, then part B says, hey, here's a new sequence. And the new sequence is defined as follows. The sequence is called B. The nth term of the B sequence is the reciprocal of the reciprocal of an element of the Fibonacci sequence and the previous elements. Okay, that's fine. Then it says, all right, write out the first 12 terms of the sequence. Minnie, can you hook your calculator up to the TV and turn the TV on and hit the TV video button? So what is this? Well, I think it's just a matter of applying the thing. It's that over that. So that's 1, and then it's 2, and then it's 3 halves, 5 thirds, 8 fifths, 13 eighths, etc. How far do I have to go?
Did it say n greater than 2?
I think it said n greater than 1.
Yes.
Oh, so I should get rid of the 1? Is that what you're trying to say? Okay, so we can just get rid of the 1. So it's 34 over 21, 55. Tell me when I can stop.
Go all the way to
Yo, Mr. Rose.
Yo.
The TV thingy.
Yeah. Someone do it. No. Just know what to do and just do it and be done already.
Jamie, turn it on.
Plug the thing into the thing and turn the TV on. Haven't we been through this all before?
No.
Maybe.
With your calculator.
No.
Press
Grab the
every
remote.
single button in the
Turn the
one.
remote, turn the TV on. Good. Now find the thing that goes into the thing. Turn the line down. Turn the line down. Stop, turn the line down.
What?
Turn the line down. There's a cord. See that?
Is it the white one?
Haven't we been through this already? I thought we've been through this already.
No.
No, it's somewhere. It's that one. It's the one that's over kind of on the ground. Yeah, that one. No, the white one. The white cord. Yeah, grab that. Keep following that all the way along. Yup. Now you need to hit the TV video button on the remote. Plug that in. Plug it into the top. hit the TV. This is a riveting video. Hit the TV video button on the remote. Plug that in. Turn the calculator on. Are we ready to go? Oh my god.
You know, you should have set this
The
up
one that says
before.
TV video. All right. Good. Okay. So when something exciting happens on the screen, you have to turn around and look at it with the camera. Okay. So this is the sequence. So far, this problem has been completely mindless. Then part C actually asked you to do some actual math. It said prove the following recursive relation. Show that b sub n is in fact 1 plus 1 over b sub n minus 1. Okay, well, this is really just some kind of like mindless trig identity, right? So let's just do it. To start with one side,
Trig identity.
it is a trig identity-like operation. It's just like kind of do it, right? Just show that the left side equals the right side. So let's just start with the right side because that's the more complicated one, and hopefully I can just transform it into this. All right, well, I begin. What is 1 plus 1 over b sub n minus 1? Well, I will use the definition of b sub n minus 1. B sub n minus 1 is just that, right? So it's going to be 1 plus 1 over a sub n over a sub n minus 1. Do you agree? Yeah, and then that can just like some algebra 1 happens. So that's really 1 plus a sub n minus 1 over a sub n. Okay, what now? Well, I can do common denominator. So this is really a sub n plus a sub n minus 1 over a sub n. And now I notice something. This numerator is actually just b sub n, a sub n plus 1. Yeah, duh. A sub n plus 1 by the definition of Fibonacci. And that is by the definition of b sub n. So that's basically it. Okay. However, there's more to this problem. There's a part D, Rose part D, which I did not assign, which we're going to do now, which is what is going on here. In particular, so because this is functions, I can count on at least 5 or 6 people already knowing this. What are these numbers? In fact, let's just do the thing. So whoever has control of Minnie's calculator, please take control at the moment of it. Sitting over
Should I
there.
turn it on?
So what?
Can you like then draw the
Okay, good. So let's start. What we are doing is, according to what we just proved, what we have just learned is that I can generate the next term of this sequence by doing 1 plus 1 over the previous term. Okay, so the first term of b is 2. So hit 2, enter. And now type 1 plus 1 over answer. 1 over answer, enter. And that's going to give the next number, right? And then because it's just a calculator, you can just enter, and it's going to again do 1 plus 1 over answer. That's 5/3. Everyone following this? Yes. Oh, so exciting. Hit enter again. Man, that's 8/5. Enter again. That's 13/8. Enter again. That's 21/13. Everybody knows that. Right, keep hitting enter, like, until, like, yeah, just keep going. Oh! No.
It's like
more. Okay, I'm still not quite recognizing it. Oh yes, now I see. What is this? This appears to be, okay, you can probably stop now because we've gone past the digits that the calculator will allow. What is this number? Yeah, I think that this is phi. So conjecture, this sequence ends up in phi, or has a limit of phi or something like that, which is what we're going to talk about in like 10 minutes. So how can I prove that this is true? Well, yeah, how do I prove that this is true? Yeah.
Basically the continued fraction of 1 plus.
It is basically the continued fraction form of phi. Yes, recall, how did we define phi? Okay, well, you probably did it some kind of like golden rectangle like type crap. Ooh, that's not looking so good. So, a little bit of that, and yeah, sure. So, phi is the ratio between the long and short side of a golden rectangle, which is a rectangle which you can take a square off and a rectangle remains. And so, or the rectangle that remains is similar to the original. So if the rectangle that remains is similar to the original, then x plus 1 is the long is to the short as the long is to the short. And so, yeah, we just get x squared equals x plus 1, and when we solve this, we end up with phi, which is 1 plus root 5 over 2. Okay, so, yeah. So, interesting properties of phi. One property of phi is just that phi squared equals phi plus 1, because, duh, phi is the positive solution to, or it's the larger of the two, no, it's the positive one. It's the positive solution to this equation. Another way of phrasing that is to, well, you can take this and you can kind of divide by phi. So you get that phi is 1 over phi, no, phi is 1 plus 1 over phi. And so, in fact, we have this thing that says that the reciprocal of phi is just phi minus 1. So these are like two really cool facts about phi, that when you square it, you get something which is 1 more than itself, and its reciprocal is 1 less than itself. Okay, well, says Sambuda, oh, actually we did this. What am I talking about? We did this actually, right?
Yeah.
Yeah, we did that. I'm wasting all this time. We did the continued fraction expansion of phi. I forgot this was a function. So yeah, what is the continued fraction expansion of phi? Well, we said that, hey, since phi is just 1 plus 1 over phi, then if phi is 1 plus 1 over phi, then phi is 1 plus 1 over 1 plus 1 over phi. And phi is therefore 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1. So, how does that relate to what's going on here? Why should I? Well, this is what we just proved about this sequence, that it has this relation. And so what am I really doing? I'm starting with the number 2, and I'm reciprocating adding 1. Reciprocating adding 1, reciprocating add 1, reciprocating add 1. And so if you want to think about how this sequence is formed, it's like I start with the 2, and then according to this recursive rule, I should reciprocate add 1. Then what do? Reciprocate add 1. Reciprocate add 1. Reciprocate add 1. And hopefully you can see that this is, the more you do that, the more this is looking like phi-like. Alright, so that's a kind of a loose proof of that. Alright, that problem was pretty fun. More problems from section 9.2 and 9.3. Anything that are more or less just kind of like algebra 2-ish type, like do this, learn the rule. There are a couple that are kind of hard, I don't know, Lawrence, Joshua, and Bar.
67B.
67B from which section?
9.2.
Section 9.2, 67B. Oh man, I gotta like do stuff. 67. A person accepts a position with a company and will receive a salary of $27,500. For the first year, the person is guaranteed to raise $1,500 per year for the next 5 years. So then, this is kind of like a sequence in which A sub 1 is 2750 and D is, I'll call it D sub 1, is 1,500. And then determine the person's salary during the 6th year of employment. Okay, I don't feel like doing that. Determine the person's total compensation with the company through 6 full years of employment. Well, that's just S sub 6, right? So it's just a giant, it's like big numbers. They're too big. Can't do it. This is like N over 2 times the first term plus N minus 1, so that's 5 times D. So it's just that number, whatever that is. Am I doing this right? I think so. Other questions? Okay, good. Can I have this homework? All 3 pieces of this homework. I expect everyone now is an expert on sequences, arithmetic, and oh.
Can you go over one more?
Oh man. Wait, hold on. Pause with the handing in process. Calvin and others are requesting one more problem, which was, what was it? Section 9.3, number 6. 16.
6B, the
6-0.
last question.
Oh, 6-0. Oh, this one's cool.
Oh yeah, this is like very the famous problem.
This is like some kind of, what's that called?
I'm gonna
It's like a fractal. The sides of a square are 16 inches in length. The square is divided into 9 smaller squares, and the center square is shaded. Each of the 8 unshaded squares is then divided into 9 smaller squares, and the center square of each is shaded. It's a little bit annoying in the book because shading is like gray, but unshaded is blue, so that's questionable. If this process is repeated 4 more times, determine the area of the shaded region. Wait, okay. 4? I think that's what it said, right? Yeah.
You're in the shot.
So in the original square, let's call this 1. What is the area of the shaded region? No, trick question. Wait, hold on, am I doing this right? The square is divided into 9 smaller squares and the center square is shaded. So here the area of the shaded square is 0. Right? Because none is shaded. Stay with me, class. Yo, agree? Ishan, agree? Okay, then in the second step of the algorithm, the middle square is shaded. So now, how much is shaded? 1/9. And then in the, this will be fun to draw. In the next iteration, like basically that is shaded. Picture.
No, it's the full middle one. Full middle.
Oh, still. Okay. Right. Once you shade something, it stays shaded. So this is a great picture going on here. Okay, oh I see. Okay, so a little bit more thinking here is required. So how much is shaded now? Okay, wait, hold on. Okay, so now it's, okay, so the lame way to do it would be to say that it's how much was previously shaded plus, so it's sort of like 1/9 plus 1/9 of 8/9. Right?
Yeah.
Which is this actually the way to do it? 8/81 plus 9/17. No, but I think there's a better way. So what is that? So this is 17/81. I thought there was a cooler way to do this. There is, if you factor out a 1/9. So if you factor out a 1/9, then this is 1 plus 8/9. So that's 17/9. I think it's just multiplying by 17/9 each time, right? Because now in the next one, which I won't draw because it's too hard, in the next one, what is it? Well, it's the previous number. So let's just, so let's call this ace of 1. Let's call this ace of 2. No one appears to be helping me. Let's call this ace of 3. So now what's ace of 4? Ace of 4 is ace of 3 plus, what's wrong? I think this is right. This is right, I think. Am I doing arithmetic wrong?
No.
No.
But your idea was.
There's some cooler way to do this. But suddenly I can't remember.
I mean, in general.
Hey, couldn't
You
you
can do it
like
in
count the
general,
white?
really.
You could just
easily.
consider like the amount shaded every time, like in addition, and then add them up, like with the
Geometric.
geometric series.
That's
Like
like
one
the
Oh,
whole
are you going to
Probably.
figure out how much of the places like unshaded?
No.
Outside.
Okay, I like this idea better. That's kind of what I was doing, but I wasn't explaining it well. So let's try this again. So basically, okay. So yeah, let's do it this way. Let's draw a picture of how much, let's make the sequence how much was newly shaded in each step. Yeah. So in this step, 1/9 was shaded. In this step only, how much new stuff was shaded? Well, 1/9 of 8/9. Okay, then in the next step, how much will be shaded? Well, 1/9 of what remains unshaded, which is
8/9 squared.
8/9 of 8/9. I still feel like there was a better way to do this, but this works. So I'm not going to draw it now, right? But if you see here, we shaded one box, so 8/9 remains unshaded. Here we shaded 8/9, or we shaded 1/9 of the remaining. Here we shade 1/9 of the remaining. And so we see that each time we just multiply by 8/9.
We should work for
And now we just have to count. We say 9 smaller squares, the squares each shaded. So now we just have to count how many in the same square shaded. So that's one shade. Shade again 4 more times. So 6 shadings happen. So if 6 shadings happen, starting with this being the first one, then really what we have is the sequence 1/9, 1/9 times 8/9, 1/9 times 8/9 squared. It's probably harder than I thought. And then we want the 6th one. So that's 1/9 times 8/9 to the 5th. And then if we just sum all of those, that'll be the right answer. Yes?
Well, I'm not exactly sure if this is right, but if you just do the sequence for the amount of white instead of the amount of
Yeah.
shaded.
I realized that about 45 seconds ago. Yes, the cooler way to do this, which I was hoping someone would suggest, but now, Sophia finally did, is that the problem works out cooler if you just keep track of what's unshaded. Then it's just an easier problem. But I think what I did was correct. You'll have to just sum up those things. But yeah, if you keep track of what was unshaded and how much here is unshaded. 8/9 is unshaded. And then on the next time, how much is unshaded?
64.
8/9 of that, right? Yeah. So it's just 8/9 squared. I think that's right. 8/9 of 8/9. Yeah. Each time you don't shade 8/9 of the remaining. So this will be 8/9 cubed, and then you eventually get to 8/9 to the 6th. Yeah. And so then when you're all done, so then this is actually just the answer, right? This final number is the total amount unshaded after the last one, so you do 1 minus that. So the answer is 1 minus 8/9 to the 6th. I can't believe we're taking this whole stupid problem. Yes?
As you go like towards infinity,
Yeah, I thought that was the problem.
That was not the problem.
yeah.
But that is a good transition to what we're going to be doing now, which is talking about what happens as you go to infinity. What time do we actually have?
Well, that was my answer.
20 minutes.
This entire thing.
Not really enough time. Nonetheless, we will do it. Okay. So I'll flip that thing around. We're going to talk about some stuff now. So, in fact, what I would like to now do is develop. A precise mathematical way to talk about what happens as a sequence continues indefinitely. Okay, let's take a particular sequence. Let's take the sequence a sub n equals 1 over 2 to the n. Now, as we discussed, a sequence is really like a function whose domain is the positive integers. So we can make a graph of this sequence just like we would make a graph of any function. What is the first term of this sequence?
Mr. Rose, do you still want us to handle the homework?
Yeah, but now I'm going to just do that later. What is the first term of this sequence? Everybody?
1/2.
1/2, thank you. So when I plug in a 1, I get a 1/2. What is the second term of the sequence? 1/4. what is the third term of the sequence?
1/8.
1/8. And we get a little bit of like stuff like that. Okay, so would someone like to make a conjecture about what happens to this sequence as n goes to infinity? Stan Buddha.
I think it approaches 0.
I think it also approaches 0. So what I would like to discuss right now is what that exactly means. And for this, we're going to bring out the big guns, and we're going to use the L word. So we're basically doing calculus today. So what we say is that the limit as n goes to infinity of this sequence, 1 over 2 to the n, is 0. What we mean when we say this is exactly what you already intuitively felt was true. That as the terms grow larger and larger, as n grows larger and larger, the terms get closer and closer to 0. Okay. Unfortunately, this is a tricky concept. To make very precise what we mean by that, it's kind of hard. So let's look at another example. Let's just move on to another example. Because this example is okay, but I like another one better. So let's take the limit as n goes to infinity of 3 plus -1 to the n over n. Okay, take 5 seconds and think about that, and please give me a conjecture of what you think this limit is. Kusal? 3. Where did you get that from? Well, he probably did something like this in his head. Let's make a graph.
I didn't make a
of this. So 1, 2, 3, 4, something like this. When I plug in n equals 1, what do I get? I get 2. When I plug in n equals 2, what do I get? Yeah, I get 3 plus a half. So that's like there. When I plug in 3, what do I get? 3 minus a third. And so indeed, it seems as if the answers are always going to kind of hover around 3, right? When I plug in 4, I get 3 plus a fourth. When I plug in 5, I get 3 minus a fifth, etc. And so these numbers are going to kind of bounce along, but it does appear that as n gets larger and larger, that the terms of the sequence get really, really close to 3. All right, so what I would like to do now is engage in a little activity in which and the point of this activity is for us to tease out our precise meaning of what is it that we really are saying when we say that this limit is 3. Okay, so we're going to play basically the quantifier game. The quantifier game is like this. I will defend this claim. Okay, so I'm the hero of the story because I'm right. This is 3. You are the skeptics who are holding me back, though performing a valuable social function, skeptics. So you have to just be, so who would like, I always usually pick one person. Who would like to fight with me in a,
Stephen Miller.
Where's David?
I think you should pick Lyndon.
That's tempting, but no. Yeah, David Miller, he's not here, so we'll just do, let's see, we'll do antibiotics. So you have to fight me. Now you have to fight in a rational, respectful way, but you have to just skeptically not accept anything I'm saying, okay? So, alright, so here we go. I say that the limit of 3 plus -1 to n over n is 3.
No.
Okay, good. She says no, that's a good first start. Okay, no, seriously, it's 3. Say something like, I don't believe you.
I don't believe you.
Okay, no, really, it's 3.
This game feels rigged.
Okay, why? That's a good follow-up question. No, it's too late. She's doing that all the time. You can suggest something to her. So.
What if infinity is not an integer?
Okay, wait, hold on. No, but it is. We're not getting to that yet. Okay, hold on. Okay, Annabart said why. Okay, Annabart, let's. So here's why. Or maybe even you could say like, what does that even mean?
What does that mean?
Well, what that means is that as n as n gets bigger and bigger, the terms of this sequence get closer and closer to 3.
How do you know?
Oh, good. All right, let's take it from the top. We need to repeat this a couple times. So we're working on our script. Okay, so we'll start again. The limit is n approaching infinity of this sequence is 3.
No.
No, seriously, the limit of the sequence is 3.
What does that mean?
Well, that means that as n gets larger and larger, the terms of this sequence get closer and closer to 3.
How do you know?
No, they do. They get closer and closer to 3. They get really, really close to 3.
Prove it.
What seems like a reasonable thing for her to ask now? I just say that the terms get really, really, really close to 3.
What happens
How
if
close?
it's like 0
How
or
close?
really small?
Yeah, how close? And how close? That seems like a reasonable question. If I think that the terms are getting really, really close to 3, then a question for you might be,
How close?
how close? Yeah, that's a good question. Okay, second from the top. So the limit of this sequence is 3.
I disagree.
No, seriously, it's 3.
What does that mean?
Oh, that means that as n gets larger and larger,
Do you have a eureka moment?
that means that as n gets larger and larger, the terms of this sequence get closer and closer to 3.
How do you know?
They do. They get really, really close to 3.
How close?
Oh, she's challenging me now. This is the essence of the quantifier game, is that she's challenging me. She says, how close? Okay, watch how I now turn the tables on her dramatically. Hannah Barb, the answer to your question of how close is as close as you want.
How close do I want it?
I can get as close to 3 as you want. Pick up a number. You can't say 0. Pick a, because it doesn't get, because they in fact it's never 0. But that's not part of my claim. My claim is that I can get as close to 3 as you might possibly desire. Pick a very small positive number. How about like 1/10?
10 to the negative.
How about 1/10? Okay, Anna Bart, it doesn't matter what number you pick. I'm going to still win. So suppose Anna Bart picks 1/10. Okay, she challenges me with 1/10. Her challenge is, remember, to quickly recap the conversation, I say the term's getting closer and closer to 3. She says, how close? I say, as close as you want. She says 1/10. So if she says 1/10, what she's doing is she is challenging me to get actually within 1/10. And what do I have to do to meet that challenge? Everyone's talking at once? What do I have to do to meet the challenge? Remember, she's proposing 1/10. So what do I have to do to meet that challenge? Amy?
You have to find an a of n such that the negative 1 to the nth over n term is its absolute value is smaller than or equal to 1/10.
Yes, I think you basically said that right. Can I rephrase? I'm going to rephrase I think I'm going to try to rephrase what you just said, which is I have to find some term